Nuclear transformations, actually, you're going to read it from your textbook. We've touched upon these ideas interspersed in the discussion, um, but just reading it from the textbook should be enough. Uh, and instead of discussing that, we're going to talk about radioactive dating. It's in parentheses here because that's not the actual subtitle in the textbook for that section. Um, One of the things that I've mentioned, I believe, a couple of times already, is that hopefully this class is going to help you develop skills to learn uh, independently and to learn from reading your textbook and consuming other sources of information. So one of the things that I want you to do is when you come across an equation, a mathematical equation, to again interrogate that equation the same way that we interrogate plots and graphs and figures, and ask yourself, what is this question telling me? What information can I draw from this equation? Equations are mathematical models that we use as tools, and often we use them to predict something. So let's look at these two equations that we introduced before. The top one, we have that a half-life equals the natural log of 2 over k. So half-life and k are both constants and they're related. So if we know one, we know the other. And it may be that finding the half-life, the time it takes for a sample to drop its concentration to 1/2, is a lot easier. It may be that's easier than finding k. So we use that, the one that's easy to calculate or find, determine, to find the one that's more difficult. And then we have this other expression down here, which we derived. You don't need to understand the math at this point, but we derived from our kinetics introduction, where we have the natural log of the number of particles at a given time over the number of particles originally present in the sample equals minus the constant times the time that has elapsed. What can we get from this equation? So we can tell, if we know how much we had initially and we know the time that has passed by, we can find how much we have left of that sample. Or if we know how much we had initially and how much we have now, we can find that ratio, and from that we can find the time that has elapsed. And similarly, you showed that in one of your stop and practice exercises, you showed that it is equivalent using the rates of the reaction, the decay at a given time, and the original rate, using that ratio is equivalent to using the number of particles. Okay, we're going to use these equations for what we call radiometric dating. And the first example we're going to use, probably you've heard more about this one than others, is carbon-14. To understand carbon-14, the radiometric analysis or determination using carbon-14, we need to establish a couple of ideas. First, that the ratio of carbon-14, which is radioactive, to carbon-12, which is not radioactive, that ratio is a constant in the atmosphere. Okay, we'll see where that comes from, but at the time being, we're going to say that is a constant. Now, living organisms, we integrate carbon from the atmosphere. I'm not going to go into details about the carbon cycle and anything of that because you know it already. But what's important from the chemical perspective here is that we interact chemically with the environment, living creatures, organisms, and in such a way that we reach equilibrium, integrating carbon in our tissues, so that that ratio of carbon-14 to carbon-12, in this case I chose a cat. In the cat, is the same as it is in the surroundings, in the atmosphere. Okay, that's relevant. That's very important. So if we look at the cat, or if we look at a tree around the cat, or just in the atmosphere, or any other um, living creature, the ratio of carbon-14 to carbon-12 is going to be the same, because the systems are at equilibrium through that exchange. Now, let's kill the cat. What happens? When the poor thing dies, that exchange with the environment stops. So the ratio in the atmosphere or in the environment, in the surroundings, that ratio is going to remain constant. But the carbon-14 in the dead cat will decay, it will decompose. So what's going to happen to this ratio? The ratio is going to get smaller. And the longer the time, the smaller that ratio. And we can use that to tell when the poor thing died. We may not be able to tell who killed the cat. That's for the next chapter. But we can tell when it died. Okay, a little bit more of nuclear chemistry here. The reason why the carbon-14, carbon-12 ratio in the atmosphere or in the environment is constant is because the higher layers of the atmosphere, I think it's called the troposphere, is bombarded with cosmic rays, and neutrons react with nitrogen-14 and create the carbon-14. That's constantly happening. So carbon-14 is being decomposed, decays in the planet, but it's being replenished because of the bombardment of cosmic rays on the atmosphere. So we have that production of carbon-14 and consumption of carbon-14 reaches an equilibrium, and that's what we say the ratio is constant in the atmosphere and in the environment. Cat dies, and the content in the cat, in the tissues, continues decaying. It's not being replenished because there's no exchange with the environment, and that ratio goes down. Neat. Because, for instance, if we go in and we measure the ratio of carbon-14 to carbon-12, where is it? Here, in the dead cat, and we see that that corresponds to 1/4 of the ratio of carbon-14 to carbon-12 in the environment, in the atmosphere. If it is 1/4, we have a good idea of what time has passed. Okay? If it goes down to 1/2, we would call that a half-life. If it goes down to 1/4, that would be 2 half-lives. And we know the half-life for carbon-14 because it's a constant. Of course, I'm using here a very immediate example, but that can be any value. So that explains how we use carbon-14 for dating, but radiometric dating, but evidently there are going to be some limitations to the use of carbon-14, and what I would suggest you to do is extract those possible limitations from your reading, and you already have an idea of what limitations may be just from my beautiful diagrams here of a live cat and a dead cat. Now, again, another hint on the limitations of the use of carbon-14. Let's say we have rocks. I don't know, we could look at the carbon-14 of a rock. But let's say we have rocks. And let's say we cannot use carbon-14. So we're going to use uranium-238, which decomposes to lead-206. We have this rock that we find today somewhere in the garden, and we wonder when that rock was formed. So time today, time 0. At time 0, we're going to say that the rock contained a given amount of uranium-238, which we're going to call N sub 0. And we're going to assume, it's a very, very safe assumption, that there was no lead present when the rock was formed. No lead-206 when the rock was formed. As time passed, some of that uranium reacted, it decomposed. So at time today, we're going to have a number of uranium nuclides, 238, that's going to be smaller, and we're going to call that N. And now, since uranium decomposed, we're going to have some lead present, lead-206. So uranium N sub 0 at the beginning, N today, lead nothing at the beginning, some today. How much are we going to have of lead? For each nuclide of uranium that reacted, we're going to get 1 nuclide of lead. So there's a direct relationship. And we know that, therefore, that the total amount initially is going to be the same, or it's going to be equal to whatever is left unreacted plus the number of nuclides that reacted to form whatever we have of lead present today. Okay. So if we measure the content today, that's N, and use basic stoichiometry, we can find the amount that was present originally. What's that basic stoichiometry? 1-to-1 reaction for lead and uranium. For each lead nuclide that we find today, we know that originally there was 1 uranium nuclide. If we have N sub 0 and we have N, all we need to do is plug in our values in this equation and we get the time that has passed by because K is a constant. Now, stop and practice. Let's say we have a skull and it has a decay rate for carbon-14 that's 0.85 disintegrations per minute. And let's say that the decay in the environment is 15.3, which we said would be a constant throughout history. They give you the value for the half-life. You need to find out the age of that skull. Okay, so you have the rate, decay rate, which we said we could use instead of the number of particles. It's proportional. And the half-life. Now here we have a sample of plutonium-236, and that is 2.88 milligrams. And they give you the constant, the rate constant here, and they give you different questions for which essentially we're going to use these equations here and solve for the unknowns. And this here is just again a summary of what we said about carbon-14. And I want to point out a common mistake here. When you use the mass at 2 different times, you need to make certain that you're using mass of the same substance. If you divide, for instance, the mass of uranium-238 over the mass of lead-206, the units would not cancel out. Your dimensional analysis wouldn't work, and your result is going to be off. Okay, so make sure that you're using corresponding values. Mass, initial mass of uranium, final mass of uranium, for instance, and do dimensional analysis. And this is a solved problem. Yeah. For your practice. And next video, we're going to talk about thermodynamic stability of the nucleus.